And let's wait for 1 or 2 minutes. All right, let's get started. Hello, everyone. Welcome to the 6th UQM summer seminar. Today, we're very happy to have Yizhi You from Princeton University and Yizhi You from University of Chicago. Yizhi is the first speaker, and she will talk about subsystem symmetry-enabled HOTI and its topological phase transitions. Yizhi, you can take over.
Yeah, thanks. Thanks, Zhuxi, for the introduction. Today, I will talk about a higher-order topological insulator in the strongly interacting region, which is protected by subsystem symmetry. And I will also mention some exotic topological phase transition between such kind of higher-order topological insulator toward a trivial Mott insulator phase. So now let's begin with a simple and pedagogical introduction on what does it mean by a higher order topological insulator, although I believe most people in the audience here already heard about it or know very well about it. So for the usual prominent examples of topological insulator in the weakly interacting region, we know it refers to one kind of charge insulator where the charge degree of freedom is fully gapped in the bulk. However, in the presence of boundary, we will have some gapless degree of freedom living on the surface protected by symmetries, and there's also some symmetry anomaly which appear at the boundary. So that is the usual definition of ordinary TI. And the definition of higher order topological insulator is actually pretty phenomenological. It actually refers to a certain type of charge insulator where the charge degree of freedom is fully gapped in the bulk, and they are also fully gapped in most regions on the boundary or on the surface. However, at some corners, high symmetric corners or hinges which live at high symmetric lines, we will figure out that these corners or hinges contain some gapless lower dimensional mode which cannot be gapped out in the presence of a certain symmetry. Usually it's a spatial symmetries. So for example, the first example of topological quadrupole insulator is a charge insulator where the charge degree of freedom is fully gapped on the bulk and also gapped on most region of the boundary. But actually at this corner, we will figure out there's a charge zero mode living there and that is protected and being robust. And also in 3D, there's a higher order TI where the bulk and the side faces are fully gapped, but at hinges, there are some chiral 1D fermion mode, which cannot be fully gapped out. So today we will look into some higher strongly interacting limit of these higher order TI. And one question we want to answer is, from our previous introduction, it seems that these higher order topological insulator phenomenon is a descendant or extension of the well-known topological crystalline insulator, or say spatial symmetry protected topological insulator, which also supports some gapless mode living at a corner. And the reason is pretty straight. If we have a topological insulator which is barely protected by some internal symmetry like time reversal, charge U1 or whatever, and then at a boundary, there's a gapless degree of freedom, And the reason why we cannot fully gap them out is whenever we write down a mass term which has a tendency to gap out the metallic surface, we will find such kind of mass term is not invariant under the symmetry constraint. And that implies any kind of mass term, either a fermion bilinear mass in the band theory or a many-body mass, is not allowed. However, for a spatial symmetry or say crystalline symmetry protected topological insulator, the situation is in most region, we can write down a mass term which opens a gap for the metallic surface. However, under some crystalline symmetry or say spatial symmetry constraint, what we will find is under a spatial symmetry like inversion or C4 rotation, these boundary mass term must change their sign. And that implies if we have a corner which live on a high symmetric point, say inversion symmetric point, then at both sides of the inversion plane, these mass have to have opposite signs, and hence at a corner, this forms a topological defect, which is a domain wall of your boundary mass. And such kind of domain wall of the boundary mass can again trap some zero mode living at a corner here. So this is the origin of some corner mode for the topological crystalline insulator. So one question we actually want to ask is, does all of these higher order topological insulator with a protected corner mode belong to a descendant or just a trivial extension of the topological crystalline insulators? Or can we find some interesting examples which is beyond the topological crystalline insulator regime? And today, actually, I will introduce a simple model for higher order topological insulator, which is actually protected by subsystem symmetry, where the charge degree of freedom is preserved on each subsystem on rows and columns. And such kind of higher order topological insulator is pretty exotic in the sense that they don't have any non-interacting fermion or free fermion analogy. And such kind of higher order topological insulator can only exist in a strongly interacting regime. And for the second part of my talk, I will report an interesting quantum phase transition in two spatial dimensions, which drives a higher order topological insulator phase toward a trivial Mott insulator phase. And both phases have the same symmetry structures, so such kind of phase transition cannot be described within the Ginzburg-Landau-Wilson paradigm. And we find there are lots of exotic features in such kind of quantum critical point, which I will elaborate later. So now let's begin with the higher order topological insulator I want to introduce today. So it's a simple, exactly solvable model in two spatial dimensions on a square lattice where there are 4 spin-1/2 degree of freedom in each unit cell. Because it's spin-1/2 degree of freedom, we can somehow regard them as a hard-cold boson. So later I will write most Hamiltonian in terms of the hard-cold boson language. And the Hamiltonian is pretty simple. We only have one term in the Hamiltonian, which is a ring exchange term between the 4 spins on every plaquet. So for each plaquet, we actually have a ring exchange term with A dagger A here. So this model is simple because each plaquet terms commute to each other. So this is almost a commuting projector Hamiltonian. And this ring exchange term among the 4 spins living at a corner of the plaquet has a tendency to project these 4 spins into a maximal entangled state on each plaquet. So the ground state is pretty simple. It's just a product of all plaquet entangled state between the unit cells. And because that's a commuting projector Hamiltonian, definitely there is a finite gap between the ground state and excited state. So the charge degree of freedom is fully gapped. And now let's look at the symmetry of this simple ring exchange Hamiltonian. Apart from the usual time reversal symmetry, which is presented here, both in the Hamiltonian level and in this ground state level, we actually have another symmetry. We have a subsystem U1 symmetry such that if we count the SZ quantum number on each row, X row like this, or if we count all of the SZ quantum number on each column, we'll find that the charge degree, the SZ charge, or I will call it Magnon charge later, is conserved on each X row and each Y columns. This is a stronger constraint than the usual global charge conservation. And the reason we have a stronger constraint is we only have ring exchange in the ring exchange term in the Hamiltonian. So there is no boson bilinear term between the two spins from different sides. And such kind of ring exchange term always transport a pair of particle hole boson, which forms a dipole in their perpendicular direction. And such kind of motion always preserve all of the charge on every row and every columns. So now let's look at a boundary degree of freedom. If we have a smooth boundary like this on the X boundary, we will have two dangling spins.
Sorry, Yizhi, can I have a question? So you have 4 spin 1/2 on every
unit cell. Yeah.
Looks like you have a lot more symmetry than just like subdimensional symmetries, all right?
Yes, so this is exactly solvable model, integral model, so it have more symmetry, but later we will perturb it from the exactly solvable limit.
Okay, good.
But the only symmetry I need is these two, and later we will add perturbation term. So at a smooth boundary, we have two dangling spins, which is not paired with the plaqué entangled state. And these two spins live inside the same unit cell. So any infinitesimal interaction between them will project the two dangling spin into an entangled state. So smooth boundary with two dangling spins can always be gapped out by any infinitesimal interaction. However, if we have a corner here, then we will have, each corner will have odd number of spin 1/2. And if we have a time reversal symmetry and the subsystem U1 symmetry, you will find there's always a 2-level degeneracy living at each corner. So this is something like a higher order topological insulator where your bulk degree of freedom is fully gapped and the smooth part of the boundary can also be gapped. However, at each rough boundary, or say the corner, there's a spin-on-zero mode with twofold degeneracy, which cannot be lifted.
Previous question. Do you have free boundary conditions or something else? And
it's open boundary.
Sorry?
It's open boundary.
Okay, so I think it's called, but does the answer depend on that? Or if you change the boundary conditions, you're going to get a different answer?
You mean usual smooth boundary condition or twisted boundary condition? If we just have a twisted boundary condition or usual boundary condition, all of the degree of freedom would be fully gapped, and such kind of zero mode only appear if you have open boundary condition where these boundaries are no longer.
You don't have periodic boundary conditions.
No,
right?
no.
This is an open system, so it has a boundary.
True. For periodic boundary condition, then everything is fully gapped. You just have a unique ground state.
Good. And with open boundary conditions, there could still be different boundary conditions. So you probably maybe use free boundary conditions, which means you don't impose anything on that spin of the boundary. And the question I'm asking is whether the answers depend on these boundary conditions.
So yes, so in principle, we don't need to make this cut. We can make a stair-like cut or zigzag cut. And then what we will find is at each rough part of the corner, there's a spin 1/2 degree of freedom, which is not paired with any of the nearby plaqué partner, and it is protected.
Thank you.
And actually, what we want to argue is such kind of spin 1/2 zero mode living at a corner is protected as long as we have a global time reversal symmetry and a subsystem U1 symmetry. The global time reversal symmetry requirement is pretty obvious because it's a spin 1/2 degree of freedom without time reversal symmetry. I can just polarize them in any like Z direction, and then all of the corner degeneracy would be moved away. And the reason why we need a subsystem U1 symmetry is when I define a phase or I define a higher order TI, I assume that whenever I perturbed away from any exactly solvable limit, the bulk gap cannot be closed. However, it is possible to have a boundary phase transition without affecting the bulk. So without a subsystem U1 symmetry, it is possible that this corner spin 1/2 mode and this corner spin 1/2 mode can be hybridized via an edge phase transition, which appear on the X edge. So such kind of edge phase transition would induce a gap closing, which merely appears on the boundary, but it doesn't affect the bulk physics. Or actually, without subsystem U1 symmetry, I can just decorate an AKLT chain on one of the X boundary and then totally remove this spin 1/2 mode. In the presence of such kind of subsystem U1 symmetry, you will find there's no way for you to hybridize the two corners which are isolated each other because this charge and this charge belong to different sectors. And once I couple them via an edge phase transition, or once I try to hybridize them, what you will find is you are actually violating the SZ charge constraint on this column or this columns. So both subsystem U1 symmetry and the time reversal symmetry is essential to protect such kind of corner mode. And here we don't have any crystalline symmetry or whatever. So this is one of the higher order topological insulator, which is beyond the usual topological crystalline insulator story. And this higher order topological insulator actually does not have any non-interacting or free fermion counterpart because we need a subsystem symmetry, which is a very high constraint of your symmetry. If you just have a free fermion theory, which contains some fermion bilinear term, they always break subsystem symmetry. So such kind of higher order topological insulator only exists in the strongly interacting system, which only contains some ring exchange term between different sites.
So can I ask a question?
Mm-hmm.
Let's say you had a very, very rough edge, so that there's, like a macroscopic number of these sort of corner modes all along the edge that are close. If you had local terms, so you could construct local terms that sort of couple those together. Do any of your previous statements fail if you do this?
Yeah, so you can couple them. However, how can you couple them via different sites? You cannot have XY interaction between different sites. Otherwise, you are breaking subsystem U1 symmetry explicitly. You can have ZZ interaction between different sites. Then actually you will have spontaneous symmetry breaking appear out of boundary, which break time reversal symmetry spontaneously. So yes, you always have such kind of corner mode as long as the symmetry is not broken, but it is possible that some interaction would spontaneously break the time reversal symmetry. Then there is no zero mode.
Okay, thank you very much.
Another question? Just want to make sure, did you say you don't need any crystalline symmetry to pin the locations of the gapless modes?
Exactly. However, another statement I have to make is subsystem U1 symmetry is not an internal symmetry because the generator of subsystem U1 symmetry does not commute with spatial rotation. So you cannot say subsystem U1 is a pure internal symmetry. It actually somehow intertwined with the spatial symmetry.
And the physical result is the gapless modes always appear at the corners.
True.
Thanks.
So now we are convinced that this simple model gives us a higher order topological insulator with some protected corner mode, which is pretty different from the previous no crystalline insulator. And our second task is how can we characterize such kind of model beyond the exactly solvable region? Usually if we want to characterize an interacting SPT phase, we either want to figure out whether there is a well-defined many-body invariant which can be calculated in numerical simulation or analytical approach, or we want to figure out whether we can define some quantized topological response which can potentially be probed in experiment measurement or in some numerical simulations. And here the symmetry we have is we have a subsystem U1 symmetry. So whenever we have a U1 symmetry or continuous symmetry, we probably want to gauge the symmetry and see what is the electromagnetic response and whether there is a quantized topological response. So now let's try to gauge the subsystem U1 symmetry. Remember that usually if we just have a global U1 symmetry and we gauge it, then we get a vector gauge theory. However, here we have subsystem U1, which means all of the charge on this row or whatever columns is conserved. And hence, there is no way for you to transport a single charge between one side to the other side. Such kind of motion always breaks subsystem charge conservation. And this actually implies in our low energy effective theory, there's no current operator for a single charge. So we don't have Jx or Jy current. Instead, the minimal kinetic motion allowed by subsystem symmetry is something like a ring exchange term, which can be regarded as a dipole current. So a ring exchange term actually annihilate a particle hole between this X link, which can be regarded as a dipole degree of freedom. And it actually transports this dipole, an X dipole in the direction perpendicular to their orientation. So for the ring exchange term, we can regard we are actually moving this X dipole along the Y direction, or I'm moving the y dipole along the x direction. And hence, if I gauge such kind of term, I will minimal couple with such kind of ring exchange term with a rank 2 gauge field, which I will call it AXY. Because it is a gauge connection, then we can define its gauge transformation. If we impose an arbitrary phase shift for all of the bosons on any side, and in order to make this minimal coupling gauge invariant, the gauge transformation for this rank 2 gauge field AXY is AXY can be shifted by any smooth function as partial x, partial y, alpha, where alpha is a smooth function. And in the meantime, because charge density operator is always allowed, so we should have a time component A naught term, which will minimal couple with hard-core bosons charge density. So these are the only two gauge potential term we can write down. And once we know the gauge potential term and we know their gauge transformation or say gauge structure, we will figure out what kind of gauge invariant term is allowed in your low energy effective theory. Actually, at a leading order or say topological diagram order, the only term allowed is such kind of quadrupolarization term where a quadrupole moment qxy, which is defined as the coefficient theta divided by 2 pi, is minimal with coupled with this term, which I will call it a rank 2 electric field EXY. So what does it mean by a rank 2 electric field EXY? So let's make an analogy. In the usual vector gauge theory, like 2D Maxwell theory, if we have an electric field, then and we have a single charge, then the electric field will have a tendency to say EX, then it will have a tendency to move a charge along the X direction and hence induce a charge current in X direction. And such kind of charge current can be regarded as we adding a total dipole PX to a space-time, and hence in usual electromagnetism, the electric field in I direction would minimal couple with the charge dipole density PX. And same here for this EXY term. If we have a EXY, external EXY field, and we have a dipole, which is a particle hole spatially separate along the Y direction, such kind of higher rank electric field will have a tendency to drive this Y dipole moving along X direction, moving along its perpendicular direction. Or if we have a dipole oriented in X direction, such kind of higher rank electric field will have a tendency to move it along the perpendicular Y direction. So each EXY field will have a tendency to move one dipole I along its perpendicular direction, and such kind of dipole current can be regarded as adding a quadrupole moment to our space-time, and hence the coefficient which couple with EXY is what I called a quadrupole moment. So this is actually the only gauge invariant term allowed at a topological diagram. But we don't just want a trivial electromagnetic response. We want some topological electromagnetic response, which means the coefficient of such kind of response theory have to be quantized, or at least they have to take some discrete values enforced by symmetry, and they should be pretty robust under any arbitrary perturbations or additional interactions. So the next step is to figure out whether such kind of quadrupolarization term has a quantized coefficient. And remember, the symmetry we want to impose here is subsystem and the time reversal symmetry. And first, actually, one can argue that in the presence of subsystem symmetry, such that the charge on each X row and Y column are conserved, one can prove that this theta has an ambiguity up to 2 pi, which means whenever we shift this theta by a value as an integer of 2 pi, the low energy physics would not change, and the only change to your action is your path integral have an additional e to the 2 pi times integer coefficient, which does not affect the IR physics at all. So theta has an ambiguity up to 2 pi, and such kind of 2 pi periodicity of theta is only valid if you have subsystem symmetry. And second, we have time reversal symmetry. This time reversal symmetry is primarily defined for the spin language. In the hardcore boson language, it acts more like a particle hole symmetry. And after some symmetry analysis, what we'll find is under time reversal symmetry, such kind of quadrupolarization term is odd. So theta has to be, need to shift to minus theta under time reversal symmetry. And remember, theta always have an ambiguity up to 2 pi shift. That means if we have a time reversal invariant system, then theta can only have 2 choices. Theta can only be 0 or pi, because then time reversal take 0 to 0 and pi to minus pi, which is equivalent under a 2 pi shift. So in the presence of subsystem and time reversal symmetry, there are only 2 discrete choices for theta, either 0 or pi. And actually pi corresponds to our high order topological insulator phase, and the 0 corresponds to the usual trivial mode insulator phase without a corner mode. And then we can say this is a topological response theory because theta has to be need to be some discrete values under time reversal and subsystem symmetry, and the quadrupole moment theta here is also quantized in the presence of symmetry. And let me comment 2 parts. The level quantization of theta is only presented if we have both time reversal and subsystem U1 symmetry. Both are necessary to get a quantized coefficient. The subsystem U1 symmetry give you an ambiguity such that theta shifting by 2 pi does not change the low energy physics, and time reversal symmetry make theta to minus theta. So in the presence of both symmetries, theta can only have 2 discrete choices. However, if you break a subsystem symmetry into a global U1 charge conservation, what you will find is there's no 2 pi invariance of theta. And that actually means as long as if you just have a global U1 symmetry, there's no way to argue that theta shift by 2 pi still give you the same IR physics, and hence, even in the presence of other time reversal, even spatial symmetry, there's no way for one to argue theta can only be chosen to be some discrete values. And hence, such kind of topological quadrupolarization or quantized quadrupole moment is only defined if we have subsystem symmetry or at least some dipole conservation. If you only have global U1 symmetry, like the ordinary higher order topological insulator in the weakly interacting regime, then actually the quadrupole moment is always ill-defined in 2 spatial dimensions.
Can I ask a question?
Uh-huh.
So can I think of the second point as just as saying like, if I have a global U1 symmetry but no subsystem symmetry, then I can't define that there's no, like I can't define this higher rank gauge field?
You can define higher rank gauge field, but actually what you can do is just replace this AXY in terms of partial XAY plus partial YAX, probably divide by 2, because there still be some term which is partial XEY plus partial YEX, which would minimal couple with something like QXY. But this QXY does not have any ambiguity under any integer shift, and hence there's no level quantization of QXY.
Okay, thank you.
I have a variant of this question. Imagine you take your Hamiltonian as is, you analyze the system as you did, and now you slightly perturb the Hamiltonian by small, with an operator with a small coefficient that preserves the global U1, but not the subsystem symmetry.
Yes, so I just have some bilinear term between these 2 spaces.
For example, yeah. So what is going to happen?
What is going to happen is, first, actually, we don't have this higher rank gauge theory because the gauge structure already changed. And then actually, if you just perturbed away, it seems that we still have such kind of corner mode. However, if you barely have a time reversal and a global U1 symmetry, in principle, I can hybridize these 2 spin 1/2 mode living at a 2 corner via an edge phase transitions. You can prevent that from happening by imposing some additional spatial symmetry like inversion symmetry or C4 rotation symmetry. Then that's still a higher order topological insulator, but there's no way for you to define a quantized quadrupole moment in 2 spatial dimensions if you barely have global U1 symmetry.
So would it be fair to say that the effect you mentioned will not be robust if the system is slightly perturbed by an interaction that breaks the subsystem symmetry? Would this be a correct characterization?
first, let me make sure, what are you asking? Are you asking whether such kind of corner mode or higher order topological insulator still exist, or are you asking whether we can have a well-defined quadrupole moment of this quantized quadrupolarization?
I'm asking the first of the two. So I take the system as you analyze it, and I slightly perturb it to break the subsystem symmetry. Will the answer change or not? I think you said that it's going to change.
Yes, it is going to change. If you barely have an internal symmetry, like a global U1 symmetry cross a global time reversal symmetry, there's no higher order topological insulator, although they support some other SPT, which is totally different from what we are talking about.
Sorry, the corner mode is just a spin 1/2. Spin 1/2 only needs time reversal to be stable, right? You don't need some extra.
No, but in principle, you can have an H phase transition, or you just decorate an AKLT chain on this line and this H.
Okay.
Yes, this does not break any time reversal or charge U1 whatever symmetry. However, if you have some additional inversion symmetry or C4 rotation constraint, then actually they're still protected.
Yeah, precisely. You can, if you are only allowed to add AKLT on both X and Y direction, then it's still protected.
So these two spin 1/2 are isolated, but in principle, they can hybridize via an H phase transition. The H phase transition does not close the bulk gap. In this sense, I will regard them as the same phase.
Yeah. Right, yeah, I see what you're saying, okay.
Maybe one more question. Does this model have a fermionic version?
Yes.
What changes? Or what
nothing changed because you can just replace the hardcore boson in terms of a fermion. And it is a fermion model, but there is no intrinsic fermion excitation.
And the periodicity of theta also doesn't change? No. Okay, thanks.
It's different from the 3D where periodicity can change. So now let's see what is now we have a topological quadrupolarization, and we know that theta has to take discrete values in the presence of symmetry. And what kind of effect can we predict from such kind of topological response term or field theory? And do they all capture all of the salient features of a higher order TI, which we just introduced a moment ago? So first, if we barely have this simple term and we take a saddle point equation, what we'll find is a corner defect of theta will trap a charge. And that actually means if we have a spatial configuration like this, like in this shaded blue region, theta is pi, we have a higher order TI, and in all of the other region, we have a trivial Mott insulator where theta is 0. At a corner, we have that dxd theta has a delta function living at a corner, and this would trap a charge mode which carries a half SZ charge at a corner, which means we have a spin-on-0 mode living here. This is exactly a manifestation of the corner mode of the high order topological insulator. And another effect, which I will not elaborate today, is the dipole pumping. If I regard this theta as a time variable, so at time t, we quench the Hamiltonian, so theta suddenly jump from 0 to another value, then what we'll find is under this quench procedure, we will have a dipole pumping term, which pump x dipole along the y direction, or say pump a y dipole along the transverse x direction. And this dipole pumping is highly related to the 3D fracton gauge theory with a chiral hinge state, which I will not elaborate today. So now we are going to perturb away from the exactly solvable limit. Previously, I just introduced a very simple model which only contains a ring exchange term between every plaqué. And now what I will add is I will add an additional term which still maintains the global time reversal symmetry and subsystem charge conservation on each row and each column. So the term I will add is a bond interaction between the 4 spins within the same unit cell. So this does not, these spin bilinear interaction within the unit cell does not break any subsystem or time reversal symmetry. And we just have some XY interaction between the spins inside the unit cell. So this is the Hamiltonian I want to have. I want to have a bond interaction and plaqué interactions. And here actually, there are 2 limits, which is pretty simple. First, If the Plaquet interaction dominated physics, then that's nothing but a higher order topological insulator. If the boundary interaction dominated physics, then what we have is we just have 4 spins entangled within the unit cell, and there's no entanglement between every unit cell. So the ground state is a very simple and trivial Mott insulator phase where the wave function is the product of each unit cell state. And this actually corresponds to theta equal pi state, and the other correspond to the theta equals 0 state. Now, what I want to figure out is what happens if we have a tunable parameter lambda, which tune it from 0 to infinity. So under some numerical DMRG simulation implemented by Frank Poeman and his group member, what we find is there is a continued phase transition which connect such kind of higher order topological insulator phase toward a trivial phase, and the quantum critical point appear at around the lambda equal 2.5. So this phase transition will be very exotic because on both phases we have exactly same symmetry, the same subsystem, same time reversal, and even same lattice symmetry. So this kind of phase transition is definitely beyond the Ginzburg-Landau paradigm. But let's see what happened at a quantum critical regime. So this quantum critical point can actually have a simple percolation picture. So when we're in a higher order topological insulator phase, then we actually all of the bulk have theta equal pi, and we just have corner mode. And when we are in the trivial phase, then all of the bulk have theta equals 0. And when the ring exchange term and the intraside interaction term compete each other, then at a quantum critical regime, we can imagine that both the higher order topological insulator pattern and the trivial Mott insulator pattern would coexist with phase separation in space. So the ground state wave function can be regarded as a domain wall configuration where the domain wall separate the higher order topological insulator with theta equal pi, and the white regime where theta equals 0. And at a quantum critical region, the ground state wave function is actually a superposition of all possible domain wall, which separate theta equal pi and the theta equals 0 region. Then the question is what happened at these domain wall? Because the domain wall is nothing but a phase boundary of higher order topological insulator toward a Mott insulator. At the smooth part of the domain wall, everything is fully gapped. However, at the rough part, or say the corner of the domain wall, then we will have a spin 1/2 zero mode, which live at this domain wall. So once at a quantum critical point, such kind of domain wall is strongly fluctuated, the location of spin 1/2 zero mode are also fluctuate in space-time. So we can have different resonance.
Hi, Yizhi. Sorry to interrupt. You need to wrap up in 3 minutes.
Yes. So actually what we'll find is once the domain wall tend to shrink a little bit, it will transport 2 spin-on zero mode living at a corner as a dipole in their perpendicular directions. So it transports 2 spin into this side. And at the lattice model level, this is something like a ring exchange term. And the same, if the domain wall slightly shrink with a corner, it again annihilated 3 spin-on zero mode here and created here. So in a ring exchange term, it's still some, in the lattice model, it's still something like the ring exchange term. So actually the quantum critical point can be described in terms of a dipole liquid where a single spin does not have any kinetic motions. However, all of the domain wall fluctuation would induce a spin dipole fluctuation where x dipole can only fluctuate in the y direction or y dipole can only fluctuate in x direction. So in a minimal field theory language, what we will find is the kinetic terms of these kind of bosons does not have dx dy theta term because there's no single boson kinetics. Instead, this dx dy theta term correspond to the fact that x dipole can only hold in y direction, y dipole can only hold in the x direction. So the quantum critical point is described by a critical dipole liquid where the spin-spin correlation function is actually short range. However, if we calculate this dipole-dipole correlation functions, we will find they have an algebraic decay between 2 dipoles living on the same stripe in the perpendicular directions. So at a quantum critical point, because this is something like a critical dipole liquid, what we will find is if we only focus on the low energy physics, the zero energy points of these bosons forms a branch line along kx and ky directions. So this is something like the Fermi surface in 2D. However, all of the excitation here is bosonic. And hence, actually, in our numerical simulations at a quantum critical point, we calculate the static structure factor at a quantum critical region. And what we will find is there is a zero energy line along kx, and there's also a zero energy line along the ky directions. So the quantum critical point is described by a dipole liquid with some both type of the Fermi surface, where the zero energy points forms a closed line along kx and ky direction. Another exotic feature at a quantum critical point is its entanglement entropy. Different from 1D, for 2D quantum critical point, most of them, their entanglement still obeys the area law. So the entanglement is proportional to the parameter of the boundary for the subsystem. However, for such kind of quantum critical point, which has the form of a dipole liquid, what we find is we have a entanglement entropy, which violate the area law constraint. And actually the entanglement entropy at a quantum critical point scale as L ln L, which has an additional logarithmic correction in addition to the area law part. And such kind of behavior is pretty similar to the 2D Fermi surface. The reason we have such kind of behavior is because we have excessive number of zero energy points, which forms a closed line along the kx and ky directions. So I believe I'm running out of time. So finally, I would like to thank all of my collaborators on this project. The higher order TI field theory is developed with Burnell and Hughes, and the numerical simulation for the quantum phase transition is done with Frank Poeman and his student people at Munich. All right, thank you.
Thanks, Yizhi, for the very nice talk. We already have plenty of questions during the talk, so we'll take one or two more short questions, if there is any.
I want to ask a question about the phase transition. Just by looking at the critical theory, how do I know this theory really describes this phase transition?
You mean, how do I know this theory described a quantum critical point here?
Yeah.
Yes, so this theory has two predictions. First, it is a dipole liquid, which means the zero energy point or the SZ structure factor has a branch cut along kx and ky direction. So numerically, one can calculate the static structure factor and find that there's really excessive number of zero energy point on kx and ky axis. This is slightly isotropic because we only have 8 stripe and 100 side along x direction. The second thing we can do is it's a dipole liquid theory or dipole critical metal. So we can calculate the dipole stiffness by implement a twisted boundary condition for the dipole. And then we can calculate the dipole stiffness directly in numerical simulations. And we find in the high order TI and trivial regime, there is no stiffness. And at a quantum critical point, because that's a critical dipole liquid, we have a finite stiffness, but there's no charge stiffness again.
But just from that theory, if I don't have any numerical results, how do I know that theory describes this phase transition? For example, the tuning parameter.
What do you mean?
So can you go to the other direction? There you wrote down a Lagrangian. What's the tuning parameter for this critical theory? Okay, so once you move away from such kind of critical theory, then actually you have a dual defect term, which has a tendency to either have a Plaquet entangled state on this square or have a Plaquet entangled state at the other square. So this is actually related with the defect term, which is the dual variable of this theta. And what it does is, because this is something like a Gaussian level expansion, which ignore the compactification of theta. However, once you add addition, once you consider the defect proliferations, what you will find is the defect proliferation, depending on sign, it either impose a Plaquet entangled state between the unit cell or Plaquet entangled state within the unit cell. Okay. And both terms actually breaks inversion symmetry, which is true because only quantum critical point don't have inversion symmetry breaking. Thanks.
Question? Yizhi?
So
So you said that if you say insist on inversion symmetry, then you still have these two phases. So how does relaxing the subsystem symmetry but keeping the inversion symmetry, how does that affect the transition? Does it change the universality class completely?
Yeah, so actually what I mean by inversion symmetry is if I regard this square as a enlarged plaquet, then actually on both sides it breaks inversion symmetries. And you can say if I just have a square lattice with one spin, one half degree of freedom per side, and there's no inversion symmetry breaking, then what will happen? Is that what you are asking?
Well, or maybe keep rotation symmetry.
C4 rotation. Yes.
Rotation, right? It's still protected by that. The edge modes are protected by that. So how does the transition change if you break the subsystem symmetry?
Okay, good. Actually, what happens is if you break, the reason such kind of critical point does not have additional instability is subsystem symmetry cannot be broken spontaneously in two spatial dimensions because of Mermin-Wigner thing. However, if you just have a global U1 symmetry, then it is possible that you have a instability where U1 symmetry is broken spontaneously. And actually, another numerical result last year by Poeman's group is what you'll find is the trivial phase and higher order TI phase has an intermediate region, which is similar to the 2D superfluid phase for the XY model.
And do you understand that from your Lagrangian, from your effective?
Yes. So here we only have dx dy theta because we have subsystem symmetry. Now I say I can break subsystem symmetry explicitly by hand because you have some spin bilinear term. Then we can add dx theta or dy theta by hand, and then you will have superfluid instability.
I understand. Thank you.
All right, let's move further discussions to private channels, and thank Yizhi again, and continue to the second topic.